Welcome everyone to today's presentation from the Michigan State Science Festival. This presentation is on behalf of the Mechanical Engineering Department as part of the College of Engineering at MSU. So my name is Dr. Patton Allison. I'm an assistant professor in the Mechanical Engineering Department. And today I'd like to talk to you about fire and flame. So we're going to talk about relationships in terms of combustion science between simple things like candles and then bigger, more powerful things like rocket engines. Now, my goal for this talk is related to a concept that I had an English teacher instill in me. I had an English teacher in high school named John Rupel, who would always, in every class, give a quiz. And always a question on the quiz would be, say something intelligent about X topic we were talking about in class. And so my goal is that by the end of this class, you'll have a new perspective on flames, combustion science, and now you'll also be able to say some new intelligent things and have learned new things about combustion science. So as an instructor and a professor, I work within the Mechanical Engineering Department. Mechanical engineering covers a wide range of topics, anything from manufacturing to industry, to transport systems, robotics, including some overlap with biomedical and devices like that. In particular, my work falls under kind of this section here of engines and aircraft. Within that, we can talk about aerospace engineering. Now, by training and background, I'm an aerospace engineer. I just happen to work in the mechanical engineering department. And in particular, within the department, I teach courses on aerodynamics and also on propulsion. And the research I do is within the propulsion category, particularly combustion for propulsion. So at MSU, I also run a lab called the Advanced Diagnostics and Combustion Lab. And I wear two hats, one of a combustion scientist and another one as an engineer. And in particular, we're looking at research and studies of turbulent combustion, so chaotic flames within gas turbines. And the idea is, how can we study how fuel and air mix within the engine such that they burn more efficiently and also they burn cleaner with reduced emissions? Now, we use several tools to study these things. For example, we use high-speed cameras to take pictures at thousands of frames per second to see the physics in slow motion. And we also use laser diagnostics, where we shoot lasers through the flame to interact with chemicals in the flame. And it tells us something about the structure of the flame and how it's burning. So if you have any questions about my research or combustion in general, or working in a research lab, I'd be happy to answer any of those things at the end of the presentation. So what is combustion? So combustion science is the study of combustion processes, and these are mainly reacting flows. And the reaction we're talking about is the consumption of a fuel and oxidizer mixture. So when we think about oxidizers, we think about pure O2 or even the air around us. Now, we're always taught in school our fire triangle, in which we need fuel and oxygen and a heat source to start the reaction. The reaction itself also generates heat. So as a combustion scientist, I'm really interested in the fuel and oxygen interaction. As an engineer, I care about the heat that's generated from this flame. Now, combustion plays a role pretty much everywhere in our daily lives. You know, perhaps right now your home is being heated by a gas furnace. We have gas stoves that run off natural gas. Perhaps today you're grilling outside using propane or charcoal, which is also burning through a combustion process. So in transportation, combustion is king right now, right? Internal combustion engines use fossil fuels. Gas turbine engines, of course, also use jet fuel to burn. The lights in our homes are generated at power plants by burning of fossil fuels. So combustion is a very important process, and it's an ancient technology that we're still trying to understand today. Now, within my community of combustion scientists, we don't use the word fire and flames interchangeably as we do in general. So within the combustion community, we can kind of differentiate between these two things in terms of how the reactants are handled. So in a fire, we consider that the flow of reactants is uncontrolled. So what are reactants? Our reactants are our fuel and our oxidizer. So if you think about a fire or a campfire, the fuel is coming from the wood log and the air is coming from the ambient. So me as the scientist, we don't control how the air gets into the flame or how the fuel leaves the log. right? The same thing for a fire, if it was a building fire or things of that sort, or even a candle, right? The candle, you have fuel from the wick and then air from the ambient. Now, when we talk about flames, typically we talk about controlled reaction, where the flow rates are controlled. So think about in an engine, I control the flow of air into the cylinder. Of a car, I control the injection of fuel into the cylinder as well. Same for a jet engine, where I control the flow of jet fuel into the engine and the flow of air into the engine itself. So combustion mainly concerns itself with this chemical reaction given here. And this is the one we're typically taught in school, where we say fuel plus an oxidizer burns to generate CO2 and water. It also generates things like heat and light. And light tells us a lot about the color of the flame, and it can give us some indication of how it's mixing. And the heat is what I care, like I said, about as an engineer, because I use this heat to generate things like thrust. Now, this equation is kind of a lie in that it represents the overall beginning to end of the combustion process. So at the end, we get CO2 and water. But this little arrow here hides many, many chemical steps and the production of many, many dozens of other chemical species and molecules. So the careers of thousands of combustion scientists are contained in this little arrow, right? So as we go from burning fuel and air, along the way, we generate a whole ton of other chemical reactions and molecules. And what happens is these molecules are created and then they're destroyed before we generate finally CO2 and water coming out of the flame. So within the thickness of a little flame, we have all this additional chemistry going on. You know, this reaction also doesn't really tell the full story in that we don't really talk about the emissions. So this represents complete combustion, clean combustion. So we don't talk about soot that might get generated. You know, soot are these little tiny carbon strings of carbon molecules, as well as emissions like CO, carbon monoxide, or NOx. Now, let's talk about a really simple candle here. So how does a candle work? So functionally, we have a flame, and it's now going to heat the wax. So the wax represents the fuel of the candle. This wax melts, and then the liquid fuel is absorbed up through the wick. And then within the wick itself, the heat from the flame causes this fuel to vaporize. So in the middle of the fuel, we have fuel vapor, pure fuel vapor. Now the flame can't exist here because there's too much fuel relative to the amount of oxygen. So air from the ambient has to come in and mix in order to have the flame burn. We actually end up seeing, if we look here, this kind of complicated diagram is internal to the candle flame is pure fuel vapor. The flame exists actually on the edge here. It exists on the edge of where the fuel and the air meet. So what does it happen? We can see is from the inside of the flame, we have a high fuel concentration that gets consumed into the flame. And on the other side of the flame, we have a high air concentration, and that gets consumed in the flame. And then in the center of the flame here on this little egg structure, we have very high temperature where it's burning, right? So what it actually means is that the center of the flame is hollow. But it doesn't look hollow when we look at it. And the reason why is because you're seeing light from the flame, from the back of the flame, coming through the flame. So this is why a candle flame looks full. However, though, if we were to look at a cross section, so horizontal cross section of the flame, we end up seeing here, for example, when we lower a mesh screen onto the flame, it causes a portion of the flame to extinguish. And we end up seeing is this flame only exists here on the edge, as I said, where the fuel and air have mixed properly. So the core of the flame isn't empty, we have fuel vapor there, but the flame can't burn inside that. So when you look at the flame from the side here, right, as in the picture on the right, you're seeing the light come through the flame, which is why it looks full and as if there's a light coming from the entire structure. Now, we have lots of different types of combustion processes and appearance of flames in the real world, whether it's from the afterburner of a jet engine burning jet fuel, a Bunsen flame that you may have used in high school chemistry, our stoves, the gas coming from our stoves, or even campfires. So the question is, why do these look differently and why do they behave differently? Some of it has to do with the fuel you use. So sure, wood may burn differently than jet fuel, but a lot of it has to do with how you mix the fuel in the air. When we talk about mixing, there essentially flames break down into two categories. The first category is a premixed flame. And in this case here, for a premixed flame, my fuel and my oxygen are completely mixed beforehand. So on the right here, we have the example of a Bunsen flame, the type you would use in high school or college chemistry class. So in this flame, we have a pipe leading up to the flame. And in this pipe, we have fuel and air that have already been mixed before it reaches the flame. Now, premixed flames have this interesting property in that they want to burn towards the fresh mixture. So this flame is trying to burn its way down into this tube. And the reason why it doesn't actually move down into the tube is because it's competing with the flow of gas coming out of the tube. So there's a balance between the flame wanting to move in and the gas coming out. And so when the flame is balanced, it stays stationary as it is in the picture. Now, in contrast to that, we have diffusion flames. This is very similar to how a candle works. So my fuel and my oxidizer are not mixed before the flame. So in a candle, we have air in the ambient and we have fuel in the wax. So in order for you to generate a flame and have a place where it can burn, we need then for the fuel and air to mix. And typically it just mixes by diffusion. So we have fuel vapor from the candle diffusing in with air from the ambient, and then here's where my flame can sit. Now that flame is going to be pretty stationary. It's going to stay where the mixture ratio is appropriate. Now let's take the example of having two very long tubes. So in the top tube here, I have fuel and air mixed together, so it's pre-mixed. And the bottom tube, I have fuel and air in the tube, but separated by some separator, whatever it may be. The first example here, if I light the end of this tube and have a flame here, this flame is going to want to move or propagate through this mixture. It wants to consume all of it, right? And it can because this mixture is ready to go. It's ready to burn. And we call this propagation the flame speed of the mixture. Now, for the diffusion flame, if I light the flame right here, the flame can't move to the left because there's not enough air, and it can't move to the right because there's not enough fuel. So the flame is going to sit here in the middle, right, where fuel and air are diffusing and mixing in with each other, and then it can burn. So before we move on, I'm going to do a demonstration that we're now going to cover the differences then between these two types of flames. The second thing I'm going to do is I'm going to start a second camera. So that way you guys have a different perspective. And I'm going to use this camera as a close-up camera for what I'm doing. Now, first things first, safety first. I like my eyes. I want to keep them in good condition. So I'm going to put on some goggles. So when we study these flames, often in high school or in middle school, perhaps you've used a burner like this. It's called a Bunsen burner, all right? And so this little Bunsen burner, the way this works is I have fuel coming in through here, and then I have these little slits on the side that I can open and close to change airflow. So as gas flows up through this pipe, it pulls in, because the pressure gets low in this pipe, it pulls in surrounding air. And so within this pipe, we have a pre-mix of fuel and air. Okay, so this creates a nice little triangular little flame. However, though, I want to use something a little beefier. So for that, I have this handheld torch. Okay, this is a propane torch, just simply from Home Depot. So again, the experiments I'm going to do here, guys, don't try this at home. I'm an expert in this. I do this all the time, right? And I have a background in science specifically targeting this. So this propane torch is like a high-powered version of my little Bunsen burner. So the way this works is very similar. I have a tank of propane, and I have, if you look through here, a valve that's going to allow my fuel to flow through. And then it has these little holes around the side here. So what these little holes do is as gas flows up through the tube, the pressure is going to decrease in the tube, and it's going to pull air from the ambient around me into the tube. Okay, so within this distance, it mixes the fuel and air. Now, internal to this tube is a little spark igniter. Maybe you can see in the other camera here. And this little spark internally lights the flame. So it looks something like this. So if I open up the valve here, right? When I hold down this button, it allows fuel to flow. You can maybe hear that fuel flowing. Now, you might want to adjust your speakers a little bit because it can get a little loud. So when I do light it, fuel is flowing, air is being pulled in, it mixes, and it. Now, I can adjust my fuel flow rate, which also controls my airflow rate. So I can either have a low power flame or a high power flame. Now notice that the color of this flame is a baby blue. So if I hold it up maybe against the black background, you can see it's a nice baby blue color. There's also a little bit of teal. You can see inside the tube there's a little bit of teal. If I turn it up even more powerful, you can see it gets more and more teal. Okay, so this is an example of a premixed flame, right? So now what this flame does now is it actually wants to burn back into the tube, right? But it can't. And the reason why it can't is because it's fighting the gas that's leaving the tube. And that's why the tube sits in one place, okay? So let's take an example here. I have here a plastic tube, half-inch plastic tube from Home Depot again, okay, about 6 feet in length, coiled up. Now, what I'm going to do here is I'm going to attach my little burner into the tube. Okay, so the question is, what's going to happen here, right? If I click it, am I going to have a torch flame sit right here? Am I going to burn the entrance of this tube? What I can do is if I hold down this button slightly, I can let fuel flow into the tube. So you can hear it flowing, okay? If I let some fuel flow into the tube, remember it's pulling air with it. So I'm filling the tube with a mixture of fuel and air, right? So what do you think is going to happen? Let's see. Right? So basically, because we have a full burnable mixture of fuel and air inside the tube, that flame seeks out that fresh reactant and chases it. Right? And so that flame propagates at something we call flame speed. So depending on the mixture, this flame is going to move at a particular speed. So let's try that again. Pay attention to the color of the flame too. See how it's this kind of teal baby blue color? Okay, this is something very, very particular to premixed flames. So one more time. Okay. So those are how premixed flames behave. Let's think now a little bit about the fusion flames. So I said through these little holes here, we entrain air. Now what happens if I take a little piece of Scotch tape and I block those holes? So now I've blocked the holes with Scotch tape. Okay, so now if I pull down the button, you can hear fuel flowing. If I click it though, now nothing happens, right? And why does it happen? Well, the sparker is inside this tube here, and there's no oxygen in there now. There's no air, right? So in order for this to work, we need air. So what happens now is rather than it mixing with air in here, it mixes with air out and around me. So if I want to light this, I need a secondary source. So something like a little sparking igniter like this. Okay. So if I let fuel flow, I can then light it external to me. Now, compare how this flame looks to the premix flame. Look at the color, look at the size of the flame, look at how it follows the burner. Now, if I open this little piece of tape here, I let a little bit of air leak in. Look what happens. A little more air, less air. So I can convert the flame from the diffusion flame, this nice orange flame, to a premix flame, depending on how I control where the air is mixing. Okay, so these flames obviously behave very, very differently. And we can control these flames in engineering applications based on how we mix fuel and air together. All right, let's go back to our presentation now. Okay, so we saw some particular differences between these two flames, a lot in the color, right? So let's talk about where color from flames come from. So the color we see occurs in the visible spectrum of the electromagnetic spectrum of radiated or radiation, right? So obviously all the colors we can see fall within this sort of range of wavelengths. So in flames, we saw some blue and some teal. We also saw some orange and red. So let's talk about where each of these come from. There are essentially two ways to get color from a flame. The first is chemiluminescence, which is going to be light that occurs from chemistry. So luminescence, light, chemistry. So remember how I told you before, inside the flame, we have all these other different compounds and molecules that get created? Well, in reality, what happens is that some of these compounds, for example, this little molecule here, CH star, they get excited. And when they get excited, they release photons of light. And it happens that this particular little molecule releases photons of light at around 430 nanometers, and it releases the photon that's colored blue. And so this is why we see blue in flames. So the chemistry of burning a flame generates blue light. If there's a little bit extra fuel in the mixture, sometimes we also get this little compound here called C2. This one generates light around 470 to 500 nanometers, which is a little more into teal. So that's that teal color we saw. But what about the red and orange that we see? So the red and orange we see is not from the actual chemistry of the flame. It is not chemiluminescence. Rather, it comes from soot. So when we look at soot under a microscope, soot looks like these little chains of carbon structures, these little black carbon spheres. This is what soot looks like. When these little black round particles of soot get heated to flame temperatures, they glow. So in the same way, if I take a piece of metal and I hold a fire against it, the metal glows. Soot, when it gets hot, also glows. It glows a lot in the IR, which we can't see, but it also glows a lot in this orange and red color. All right, so when you look at the flame and you see the color, orange and red is from the soot getting hot, and then blue and the sometimes kind of greenish colors is from the chemistry of the flame itself. All flames are going to emit some of this CH star. So all flames emit some sort of blue. So you can see here at the base of this candle flame, we have a little bit of blue. The problem is the light from the soot is much, much, much brighter. And so that tends to cover and mask the blue color from a flame. So the blue color is always there. It's just that sometimes it's hidden behind the bright yellow and orange of a flame. All right, let's jump now to a little bit of propulsion work, okay? So we focus a lot on the fuel and oxygen and how we mix it. But as an engineer, I really care about the heat that's generated from this flame. So if you want to go to Mars, right, we have to have a rocket that takes off from Earth. So it leaves the ground, it leaves Earth's gravity, it can transition to a flight trajectory to Mars, and it has to be able to land on Mars. So that requires a lot of thrust to move a big rocket around. So let's look at this thrust equation that we have here. So my thrust of an engine is given by this equation here. So let's talk about each of these little terms. So we have this first term here, and it has two variables. The first variable is the mass flow rate of propellant. So this is how much stuff I move through my engine. So if I want to have a lot of thrust, I need to move a lot of stuff, which is why you see these rockets with very, very large propellant tanks for both fuel and oxidizer. The other thing I need to do is move this stuff really fast. And this is where my combustion comes in, and this is where my heat comes in. Heat helps me move stuff fast. The second thing you can do is also move things at high pressure. So think about a balloon. If I blow it up and let it go, it moves a lot because of the pressure difference inside the balloon versus outside. Now, what I'm really trying to do here is take the energy containing the fuel bonds. So when I burn something, it's exothermic. I release energy from the bonds of the fuel, okay? And this is released as heat. So I can take this high temperature gas, so high thermal energy, convert it into kinetic energy, gas that's fast. And by making this velocity U very, very large, it means I'm going to get a lot of thrust out of the engine. So rocket motors and rocket engines are designed to do exactly that. So here we have the rocket engine. This is one from the space shuttle. It's also the one being used on NASA's new Space Launch System. So you can see here it has this bell nozzle shape. And so as an engineer, we've been able to design shapes that help accelerate gas flow. So in a rocket engine, I take my fuel and my oxidizer, I pump them into a chamber, my combustion chamber, and in here it burns. So now the gas gets very, very hot. The geometry of this bell-shaped nozzle is designed to take slow moving gas, so that's subsonic, so much less than the speed of sound, and accelerate it very fast. But the way it accelerates it is it has to convert the thermal energy to kinetic energy. So if we look across the nozzle here, so here in our combustion chamber, we have very high thermal energy, right? But very low kinetic energy. The gas is moving very slow. As the gas is pushed through the nozzle, right, the kinetic energy in this blue curve increases, right? So this is that high speed gas that we want to generate thrust. But as it increases, we can see from the orange line here that my temperature decreases, right? So we're converting this thermal energy into kinetic energy, right? And the only reason we can generate this kinetic energy is by having a lot of heat to be able to use, right? So this is why combustion is so critical in getting to Mars, getting to the moon, and rocket launches. All right, that's all I have for you guys today. I'd be happy to take any questions. Please, if you guys have any questions, drop it in the Q&A right now. You can ask me anything about combustion, being in college, studying engineering, the difference between a scientist and an engineer, or any of the topics that I study. So thank you for your attention, guys.